Okay, so I think we can start the discussion session. If you still need to give your papers to Carla, or you can continue while there is a presence list that's circulating at some point. Everyone got it? Okay, so please make it circulate so that everyone gets. We will do another scheme the next days. All right, so as in the previous days, we'll get questions to all the speakers. I'm just seeing Professor Stefan here now, so I'll call them all, and you can ask questions on neutrinos and dark matter, but let's just get who's remaining. So we are a bit ahead of time. We have 15 minutes, but let's use this 15 minutes to the questions. So for now, we can ask questions. Oh, Farinaldo's there. Thanks. Okay, so we can ask questions on dark matter to Farinaldo, on neutrinos to Andrea, on neutrinos to Stefan, and then Orlando. Orlando is here too. Sorry. Okay, so good. So everyone is here, so you can ask questions about everything you heard until now in the school. And things you didn't hear at school are welcome too, as you know. So let's get the first question.
I have a question for Dune. We always hear about the neutrino floor in dark matter detection, that you can distinguish the signal between a dark matter particle and a neutrino. So how could Dune deal with it?
Problem is for Dune to be a dark matter detector, if that's what you're asking, is the purity. It's impossible to get 40 kilotons of liquid argon at the level of background free and purity that you would need to achieve. I mean, there's some people who think it might actually, but it's probably very, very difficult because the background level you would have to achieve, we just can't do that. And so as a dark matter detector of that type, Dune will most likely not be contributing. Now, yeah, I mean, of course, looking at elastic neutrino interactions, so that's a story. There are dedicated experiments that do that, yeah, that measure these cross-sections. Does that answer the question? Is that what you meant? Oh, well, that would be great. If you have a dark matter background for Dune, then we'll have discovered dark matter. I would be just happy about that. Yeah. If dark matter is visible, then of course, yeah. That's even, well, it's at least as cool as looking for CP violation is too.
We learned here that Kamiokande was made to detect proton decay, not neutrino oscillations or deficits. I would be glad if Dune discovers dark matter rather than CP violation, right? So
yeah.
That would be nice.
Take whatever, we'll discover whatever it shows. That's a good point. That's why I said this at the beginning. It's actually a very good question, because in principle you would think, why don't you use these kind of detectors as dark matter detectors? They are not that different. A lot of like xenon and 1T, and so they are also liquid noble gas. And there's dark side, yeah? I mean, there are these detectors. The problem is always background. Yeah, it's like double beta decay, and for dark matter detectors, background is an enormous issue. It's very hard to get that sorted in a detector of that size.
And of course, we will hear more about the dark side and this dark matter neutrinos detectors next week. There was a question in the back, right? Usa esse aqui que eu acho que tá melhor.
Andre, I was wondering in the neutrino-matter interaction, we use a single particle Dirac equation. Is there been a study with the field in the presence of a background non-trivial?
So the answer is yes. I mean, this issue of describing propagating states inside of a background is a very healthy, well-defined field of theoretical physics, at least. You know, people do thermal field theory, for example, and people can calculate all of these. We do these very hand-wavy definitions of what we're talking about here, but there's a formal way of calculating these matter effects using quantum field theory formalisms, or again doing this finite temperature or finite density calculations. So all of this is very well defined, and I presented it in a way that I know is correct, and the approximations are good enough for the kind of effect that we're talking about. But there is a very specific set of formalisms that you can follow to calculate these. Again, matter effects are very interesting, and they can be generalized. So for example, in a supernova explosion, very early on as the neutrinos are coming out of the supernova, the neutrinos actually see a really big neutrino density. So you have to worry about the equivalent matter effects that are generated by the neutrinos themselves. This turns out to be a very complicated problem that's very hard to solve. There are matter effects, for example, in the early universe, even if you don't take into account a matter-antimatter asymmetry. So for example, if you had a background of electrons and positrons, those effects would cancel out in what I've described. But there are finite temperature effects that you have to take into account, and they also modify neutrino propagation as well. So there's a lot of different matter effects that people have identified. Most of them in a terrestrial experiment are completely useless, but in a high density environment or a very hot environment, all of these effects have to be understood. And in particular in the supernova, as Stefan mentioned, measuring the mass hierarchy by looking at the supernova neutrinos, the story of supernova neutrino flavor evolution is very complicated. There's some very robust effects, including the one that he mentioned, but if you want to try to understand how neutrinos coming out of a supernova oscillate, that's a very complicated physics question, and we're still learning how to answer that question. There are all kinds of interesting effects that could be there. There's some effects that we know are there but are very hard to calculate. So it's still a very active area of just theoretical physics research.
Question? Youssef? So I find it interesting, and sorry I didn't do this before, that when someone asks a question, unless he or she's too shy, just state your name, so we start, knowing the names of people. So I know this guy is Youssef by chance, but so if you don't mind stating your name, I think that's nice for people to meet when you ask a question. If you don't feel comfortable, don't say your name.
Okay, thanks. A question only. I have heard that they can study the interior of the Earth with neutrinos. So now you can tell us that. So what is like the idea of doing that?
Yeah, so this is a very good question. There are different aspects to this answer. So there's one thing which probably nobody will talk about, or except unless you ask, which you did. So there's this thing called geoneutrinos. So it turns out that the Earth produces neutrinos as well, not in huge amounts, but if we understand how the Earth works, which ironically we understand the sun much better than the Earth, it turns out, because the sun is very simple, the Earth is very complicated. But if we understand how the Earth works, there's a lot of radioactive materials in the Earth's crust and even a little bit below that, which are emitting neutrinos all the time. And the reason people care about this is it turns out that, and everybody should know this because it's kind of a physics 1 problem that you hear at some point when you're learning thermodynamics. The Earth actually is much warmer than it should be if it was a black body. So you can calculate the Earth's average temperature, and it's cold. And what happens is the Earth generates some heat as well by itself. So if we didn't have the sun, we would all die, but the planet would still generate some heat anyway. So one question is, how does that happen? And that's supposed to be radioactive decays in the Earth's crust, believe it or not. That generates enough heat, and then we can measure the neutrinos from that to test that model. That's one bit of information, and people, especially these reactor neutrino experiments, they are sensitive to the right energy regime where they have to see, where they can see these neutrinos coming from the Earth. In some sense, it's a background for their experiment. So that's one way in which geology and neutrino physics coexist. The other way is that in principle, I mean, I told you about matter effects. And I told you how matter effects impact how neutrinos oscillate. You can turn, so basically, we can turn the picture around and say, imagine that I knew everything about neutrinos, and then I shot a neutrino beam through the Earth, and then I saw how they oscillated. By getting that information, I could ask questions about the Earth's density. So you should be able to see in lots of quotes, you know, if you send the neutrino all the way through the Earth, there are signatures in the oscillation spectrum that tell you about what the Earth's density is. It tells you about where the density changes. So you could basically do like a tomography exam of the Earth using neutrinos. People have talked about that. And realistically, that's not so easy to do. You can talk about doing this with solar neutrinos because they come in a way that we think we understand. You could do it with supernova neutrinos if you knew a lot about supernova neutrinos, which is very hard. Or you could do it in a dedicated way, but building these accelerators that you saw in last talk, one in every different place on Earth, is very difficult. Or building the detectors, one in every place on Earth, is also very difficult. But Stefan wants to...
The first one, that's actually a very old... Lord Kelvin already realized, when they, in the 19th century, when they realized that the Earth was probably a little older than 5,000 years, they just calculated the black body spectrum and said the Earth should have cooled down, and that was a big problem at the time, why the Earth hadn't cooled down if it was really that old. And they didn't know that was the radioactivity heating it. Yeah, so this is actually quite an old question. To the neutrino tomography of the Earth, you could do this, for example, with ice cube, with an upgraded ice cube. The interesting aspect is that neutrinos are sensitive to electrons and not to protons. So you would actually not measure the density, you measure the electron density of the Earth. Why is that relevant? Because we know roughly the baryon density of the Earth from seismographic measurements. So if you then form the ratio of the electron density to the proton density, you can actually, it's not so much the density, it's the chemical composition of the center of the Earth you can determine, because that is what actually the ratio of electron density to proton density is.
Questions? Nowadays you have to be very careful when you say that the Earth is more than 5,000 years old. You have always to tell the other side. More questions?
For a question for Dune. In the supernova measurement, how Dune can distinguish from other rare neutrino events, like a really energetic cosmic ray or something like this pop on the sky and pass to Dune? So how you will distinguish? Because the signal is some seconds, right?
Yeah. So there are different aspects of this. So from beam, so the beam neutrinos are pulsed at a much smaller. So the beam from neutrinos from Fermilab doesn't come continuous. It's pulsed. It's in buckets, and this is at a completely different time scale. It's much shorter, yeah, milliseconds or something like that. Yeah. So whereas this is 10 seconds, so you can actually, when you synchronize your readout with, when the neutrinos come from Fermilab, you know that these have to be coming from the beam. Yeah, because the beam is not on all the time, basically. Yeah, but then other things outside the beam is the good question. Now, if it is a supernova relatively close, not too close, I hope, but relatively close, we'll see so many neutrinos Honestly, there will be no doubt. The problem comes, however, if it is a more distant supernova or even diffuse. There's something we call the diffuse supernova background, because you know about all these supernovas and there are neutrinos coming from all of them. There the background is a real issue. This is, so for example, there's background from intrinsic radioactivity, argon-39, there's background from other things, as you say. So then it's going to be really difficult to do that. One thing you could do is if there's, you know what, perhaps you've heard of multi-messenger astronomy. So we have to record, we can record these events for a day or two. We can't keep those data forever. But if now there is another, let's say the astronomers see a supernova in the optical spectrum, we can go back and look exactly during that time period, even though we wouldn't have seen the signal just on its own. That's basically what IceCube, by the way, also has done. And you know, there's this, you just saw these things about multi-messenger. You take a signal neutrino, you get a signal in some other, from some other source. So if you can correlate that, but it's going to be tough, yeah.
And we will hear about multi-messenger on Friday.
My question is for you two. How you are planning to discriminate the neutron signals? Because the neutron can mimic the signal of neutrinos.
I think this would be a good PhD thesis. This is going to be difficult. Neutrons are a problem for low energy physics. I have to turn around. Neutrons are a problem for low energy physics, and this is a serious issue, yeah? To discriminate a neutron, neutrons can induce background, and I think this is still a challenge to understand exactly. I mean, there are some things you can do, I guess, pulse shape discriminations, things like that, but it's going to be difficult. Vittoria, what do we do against neutrons? Yeah. Well, you see, this is a good thesis project. It's a very good question. Yeah, it's a very good question. It's a difficult background because they are very hard, you know, to see, but they can leave signals. Yeah.
I asking you because that's the same problem that is present in deep. It is an experiment placed in Snow Lab, and they have the same problem.
Neutrons are the curse of all low background experiments because they go, you know, you have a neutron somewhere, it just bounces around until it does something. You can't see it. It's really one of the most difficult backgrounds for all low background experiments to. So of course, then you could do something. What smaller experiments do, you put neutron shielding around. So if you have external neutrons, you can always, let's say you put water or something around which has a lot of hydrogen, and then you can get neutrons by that. And people have talked about this, to put a neutron shield around Dune. It's a possibility to get external neutrons which would come from the rock or whatever absorbed. It isn't really in the plan right now, but that is one thing you could do about it. Yeah. Well, it would mean we'd have to increase the cavity a little bit. To be honest, it's not really. I think it's an issue which hasn't been at the surface so much, and I think it's a very good question that you raise this, and we have to think harder about doing that. It's partially that Dune has been optimized a little more for high energy. When high energy, I mean like the GeV neutrinos, than low energy physics, and you know, probably more could be done in that direction to optimize the design. I would actually say, is this recorded? You know, but you know, this is there's still areas, it just shows there's still areas where, you know, we can improve potentially what's being done, yeah?
You're already suggesting upgrades to Dune.
Would the position resolution be enough to detect multiple scatters for neutrons?
Well, neutrons go a long way. So the problem is, you know, neutrons go meters and more, and so this is not a problem of position resolution so much, I would say, because the neutrons are not, the problem with neutrons is something else. They, as I said, they just bounce off everything, and then the signal from the, you saw that in that fake simulation from that Mali generator. The neutrons go around, and then 30 centimeters somewhere else they do something, and the problem is, how do you correlate this information to where they come from, because you don't even know, you know, you don't see any of the steps in between. So I don't think this is really a matter of position resolution, but it's a matter of the fact that these neutrons, or the problem is that the neutrons just bounce around like crazy without being visible, and then suddenly they do a nuclear, they get, let's say there's a neutron absorption somewhere, some decay happens, and that's what you see then, yeah? These are really good questions. I mean, this is like, I mean, the review committees don't ask these tough questions. Yes.
You said that SBND and the neurodetectors are searching for sterile neutrinos. How do you do that?
Okay, you have to give me some stuff for next week. I'll also give lectures next week, and I'm already worried that, you know, 2/3 of my stuff I already present anyway, but that's not a proper answer, I admit. So basically, sterile neutrinos, in principle, they can be at any mass. But there's particular interest in sterile neutrinos which have a mass of about 1 electron volt. Which is, if you look at the neutrino mass, it's actually much more, but if you look at other masses, it's actually not that much, yeah? I mean, 1 electron volt. Now, as we have seen in that oscillation equation, which you probably have seen several times, delta m squared gives the oscillation frequency. So in order to be sensitive to an additional oscillation, so the way you do this, let's say the sterile neutrino is a 4th neutrino. So it contributes to the oscillation somehow. So you have to go where the peak of your oscillation frequency is, and that depends on the delta m squared. And therefore, this would be with a very high frequency, so you have to go close. That's why you go for short baseline, yeah? So you would look at short baselines whether whether some of the neutrinos from the beam have oscillated away. And if that wasn't clear, then I'll explain it better next Monday. But that's basically what you do, and you do the same as you do here. You have a near detector, you have a far detector, you compare the neutrino flux, and then if something is inconsistent with 3 neutrinos, then there must be a 4th neutrino. Now you might ask, what happens if this neutrino is really sterile and completely decoupled from everything and doesn't even mix? Well, then we wouldn't see it. Okay, so we still have to assume the word sterile has to be always taken with a grain of salt, because sterile still means for us, we have to assume it does at least mix with the normal active neutrinos.
I have a question. How the delta value could explain the asymmetry between matter and antimatter? I mean, which process will generate the leptogenesis?
Okay, Andre.
This is a question that everybody always asks, because it is often mentioned by people giving these talks, right? That somehow...
I was really careful, by the way.
You did a very good job.
Thanks.
Yeah, and that's the right thing to say, but basically so this is a big question. I don't know if anybody's going to talk about this a little bit outside of dark matter and neutrinos, but if you start listing what are the big questions in particle physics today, you know, the top questions are going to be why neutrinos have a mass, what's the dark matter. Another question is why is there so much matter in the universe? And that's this baryogenesis question. And again, it's a very interesting question because it's one of the, I guess you could call it a failure of early universe cosmology, because early universe cosmology allows you to calculate how many baryons are left over if you're allowed to run the movie from much further back than what we normally talk about. And you make a prediction, you know, the baryon to photon ratio should be like 10 to the minus 19, and that number is actually 10 to the minus 10. So clearly something happened that changed the number by 9 orders of magnitude. And this is a very old problem. People have been thinking about this for a long time. And once upon a time, Mr. Sakharov, or people thinking about how would we generate a large matter-antimatter asymmetry in a universe that starts out with a balanced amount of matter and antimatter. So that's the question. How do you dynamically generate a matter-antimatter asymmetry given that your initial conditions are matter-antimatter symmetric? So that's the challenge. And he figured out these are the things that have to happen in order for this process to happen dynamically. And a very general statement you can make is that you need physics processes that are not in thermal equilibrium. And we know that that will happen. For example, we heard about this freeze-out processes. That's how dark matter particles go out of thermal equilibrium, for example. That's one condition. You also need physics processes that can tell baryons from antibaryons. And that's easy to see if you don't have a physics process that does that. Every time you generate a baryon, there's the equivalent process that knows how to do the opposite. So you have to have some physics process that can tell baryons from antibaryons, let's say. And then the third component of all of this is that you need CP violation. And CP violation is for a similar reason for the baryon-antibaryon thing. If CP is not violated, everything that matter does, antimatter does, equal and opposite, so you don't generate a baryon asymmetry. So that's kind of the first layer of question. So basically, we need CP violation to exist in order for this dynamical generation of baryon number to be a thing. Now, what's really fun about the standard model of particle physics as we know it before we discovered neutrino masses is that all of these Sakharov conditions could have been met, but the numbers don't work out. So there is a deviation from thermal equilibrium, but it's very, very little because it turns out the Higgs boson is too heavy. There is also CP violation in the quark sector, but that's too small because for different reasons, but the mixing angles in the quark sector are too small, so the amount of CP violation is very small. And the third condition is this baryon-antibaryon violating interactions, and it turns out that in the standard model, there are physics processes at finite temperatures that know how to do that. But quantitatively, it doesn't work, and it fails for all these different reasons. One reason is that the amount of CP violation that we've observed in the quark sector is too small. So now that we've seen non-zero neutrino masses, then we know CP can be violated in the lepton sector. So the question then becomes, how much is it violated by? And does that CP violation have something to do with the matter-antimatter symmetry of the universe? So that's the zeroth order connection to the Dune experiment. A more complicated question is, how does it relate directly to the matter-antimatter symmetry of the universe? And the answer is, we don't know if it does. And if it does, it only relates to the matter-antimatter symmetry in an indirect way. And in order for you to make any statement, you have to put this question in the context of a model. And again, there are lots and lots of models for explaining the matter-antimatter symmetry. All of them require you to invent new particles. You have to invent some new particle. The dynamics of those new particles lead to a matter-antimatter symmetry. And there are lots of ways of doing it. There's one way which is considered to be very economical, which is if you want to explain why neutrino masses are not zero, you also have to invent new particles. So there is a model, or there's lots of different models where you explain non-zero neutrino masses with the same new particles that you need to explain the matter-antimatter symmetry as well. And those new particles have CP violation in them. Now, this is the CP violation of those new particles, let's say. These are new, very heavy particles that we will never, ever get to see. And those particles have some interactions that violate CP. What we do see at the same time is the low energy manifestation of these particles, which are the neutrino masses. And then the CP violation that we observe amongst the neutrinos is it's a daughter of the CP violation that's happening at very high energies for these very heavy particles. So the challenge then becomes, how can we convince ourselves that the CP violation that we observed is a direct consequence of this very high energy CP violation? And then there are models where we can actually make a connection. So the challenge in that case would be to first convince yourself that these models are right, and then you can use them to make a connection. More likely than not, the best models are the ones that you can actually prove them wrong. You can say, oh, this model would have allowed a relationship of this type, but I can rule it out for some reason. And I think the way we will probably make a lot of progress is by process of elimination. I think there are many models which are directly testable. If we start ruling all of those out, then the number of reasonable hypotheses that will remain will be smaller, and then we'll start to believe in this connection with the neutrino mass generation. And then the CP violation will be indirect evidence that this idea is correct. But that's a very long way from establishing that it is the right answer. And I should say, this is always true in physics. You never learn what the right answer is. You always learn what the wrong answers are not. And then you go on and make progress a little bit that way, right? So all of these really nice ideas start getting ruled out, and then you end up ruling something in, let's say. So that's the general connect. I think if somebody asks you the question, the answer is the connection tends to be very indirect, but it's a very important step towards making the scenario believable, the CCP violation in the neutrino sector. But the connection is not one-to-one. For example, imagine that we found out that there's absolutely no CP violation in the neutrino sector. That, by the way, would be an amazing discovery, because that seems really special. And then in that case, if you wanted to build one of these so-called leptogenesis models, that would be an input to your model. You'd say, can I construct a leptogenesis model where there's no observable CP violation at low energies? And that will give you some guidance for your model. So it's a very, the connection is very, very loose, but whatever answer we'll get will first of all provide a lot of inspiration, and it will also tell us what kind of model challenges we have to start concentrating on. And just one last thing which I want to say is, what's nice about the leptogenesis model is that it is very difficult to prove that it's right, but it is possible to prove that it's wrong. And it's proof with an asterisk, so it's not exactly proof, but you can show, for example, that there are, if you observe a bunch of other stuff, then you might be able to convince yourself that even if leptogenesis worked, something else would happen later on in the history of the universe that would erase whatever baryon number you generated before. So imagine you learn that. So if you learn that, then you know that it can't be leptogenesis. It has to be something that happened after this other thing happened. And then we know it has nothing to do with neutrino masses. This is one. So it's a very big open question. There's a lot of information that's missing, and we will have to fill in lots and lots of gaps in order to start sort of zooming in on what are the plausible possible solutions. And I think it would be very surprising if these neutrino experiments played no role in informing what's going on with the matter-antimatter symmetry. That's a very long answer.
Good. That's the kind of things we want to explore, what we cannot do in the normal question during the courses. Other questions?
My question is for André Chu. If neutrino and antineutrino are different in matter, couldn't I just say that they are not the same particle?
That's a very good question. I will say a lot more about this. Well, not a lot because I'll run out of time, but I will say more about this tomorrow. All of these questions are really good, and I think there's and they tend to be also very confusing. So these are good questions, and the problem is they lead to a lot of confusion. So let me, I think one thing that's useful to say is let's talk about CP violation in the neutrino sector, which is a similar question that people ask in spirit. So Stefan said that he even is confused by the fact that those two statements contradict one another. So, no, okay, but it's a confusing statement. So the question is, how can you look for CP violation in the neutrino sector if it is possible that neutrinos and antineutrinos are the same? And I want to show you that the experiment that we're doing and calling it CP violation in the neutrino sector actually does not directly pertain to neutrinos. We're not talking about neutrinos, we're talking about testing CP. And the experiment is kind of like this, right? So you have a, you have a pion, you have a pi minus, and you have a, a mu minus and a neutrino. Then this neutrino comes in and it goes all the way over here, and it hits something, and it produces an electron and something else. So this is the physics process. Remember, we never get to see the neutrino. In my Gedanken experiment, we see a muon and we see an electron, and we calculate the rate for that. And in order to calculate this rate, the intermediate step is we call this thing called the neutrino oscillation probability. But clearly, I'm measuring electrons in my final state, and I'm measuring muons in my initial state, and I'm looking for this final state. So I can look for the CP conjugate of that. And that's the physics process. And this is the thing that we normally call an antineutrino. And, but notice that the neutrino thing, whatever we call it, is an intermediate state. It's not doing anything, in quotes. The process we're calculating is the rate for, mu minus, E minus production the same as the rate for mu plus, E plus production. And if CP is conserved, these rates are the same. If CP is violated, these rates are not the same. The same is true for the matter effects. The matter effects have to do with the fact that you're doing this in an environment where this is going through a bunch of stuff. And you're comparing this in an environment where this is going through also a bunch of the same kind of stuff, not the same anti-stuff. And you have to do the calculation correctly. And if you do the calculation correctly, this process is impacted in a different way from that process. So this is the big picture answer to that. The more nitty-gritty answer to the question is that when we ask about whether the neutrino is its own antiparticle, we're still not saying that, so let me back up. Let's say, what do we really know about neutrinos or neutrino objects? We know that if I have a process like this, I create an object that I call a neutrino, and that's a left-handed object to the best of our ability to make the measurement. When I have a physics process like that, this is a right-handed object, whatever I call it. I can call it a neutrino or an antineutrino or a bob. It's some object which is right-handed. This object is not the same as that one, no matter what the neutrinos are, because their helicities are different. So what we know for sure is that there is this object which is right-handed, and then there's this object which is left-handed. The left-handed object is always produced along with a negatively charged lepton. The right-handed object is always produced along with a positively charged lepton. And then, in order for us not to say too many words, we call this a neutrino and call this an antineutrino. If the neutrino is not its own antiparticle and it has a mass, then it is possible to have a right-handed neutrino as well, which has nothing to do with this object. And it's also possible to have a left-handed antineutrino as well, which has nothing to do with that object. If the neutrino is its own antiparticle, the matter-antimatter operation that you would apply to this object here would eventually get you to this object. That means that these objects would be related in a very unusual way that we normally don't refer, that we normally don't see with, say, the electron. So I think that's, I will probably try to say this again in a maybe more confusing or less confusing way tomorrow. But this is a very big question. It's very well defined, and it's very easy to get confused. So I will try to make sure that if you do get confused, it'll be for a different reason, not for this one.
Which of course also as a corollary means if they have no mass, the neutrinos, we could never devise an experiment that would distinguish whether we see a neutrino or antineutrino or left or right-handed,
Correct, yeah.
because there's no way to make that distinction. So
Yeah,
that's why.
That's also a very important point. We can only ask this question of massive particles. For a massless particle, this is a non-question. It becomes a, how many angels are in the head of a pin kind of question. It's not a physics, it's not a science question. So the mass plays a big role, and the fact that the mass is small explains why we don't know the answer to the question, because it makes the question very hard to answer.
I have a question for Rinaldo. I didn't understand why the interaction with the rate of interaction of dark matter and standard model particles should be equals to the rate of expansion in order to have a decouple of dark matter.
Hello? Yeah. So for every single particle, not just the dark matter particle, in order to determine the decoupling of that species, you have to equal the expansion rate with the interaction rate. It's just like, as I said, if you just forget about what expansion rate and interaction rate is, just think of time. Interaction rate is 1/time, and expansion rate is also 1/time. So you're just comparing times at the end. So you just want to know whether particles will have enough time to interact before the universe expands. You just think of time, and then that's what it is. So that's for every particle. It's not just for dark matter particle. Thank you.
Next question.
Dark matter was in thermal equilibrium with the standard model matter.
Perfect. That's right. So let's say that if the standard model particles were always throughout the history in thermal equilibrium, always, what would be the abundance today? 0. Because these Boltzmann suppressed, so it goes to 0. That's why they have to go out of equilibrium. That's what Andres said. So we have a leftover abundance today, some abundance of dark matter today. They have to go out of equilibrium at some point. Otherwise, it would be 0, the abundance. And again, it's not just for dark matter, for every single particle. If they always were in thermal equilibrium, their abundance today would be 0. Unless there is asymmetry, yes. So that would be the case of asymmetric dark matter that we'll see tomorrow.
Or matter-antimatter.
Antimatter, yeah, that's the point.
Questions?
It's just a basic question for that. How you when you see those tables of standard model, you see the estimate mass of the flavor neutrinos. So how you can assure those mass if you have a superposition of the mass against states, and you can measure a single mass against state? There's some way to do it.
So that's a very good question, and I'll try to answer different parts of that question. So first of all, when you see these tables of the standard model, including the one that Stefan showed, which is old, they are all old. So you should all tell your friends that the neutrino part of that table makes no sense. It's wrong, but it's still even true in the particle data book. What happens is once upon a time, people would talk about the electron neutrino mass, the muon neutrino mass, and the tau neutrino mass. None of these things exist. The electron neutrino doesn't have a mass, the muon neutrino doesn't have a mass, and the tau neutrino doesn't have a mass. They're all linear combinations of neutrinos that do have a well-defined mass. That's kind of a statement number one. Nonetheless, all of these numbers that are quoted in those tables are correct because they mean something. And in particular, I guess I will probably mention this very briefly. We can measure things that we can call the electron neutrino mass or the muon neutrino mass or the tau neutrino mass. And these are not the masses of anything, but they are observables that you can define in one experiment. So if you did some of the problems that I assigned, the very first problem was to calculate the quote-unquote bound on the muon neutrino mass. This is the following very simple experiment. You measure pion decay to the best of your ability. You measure everything that you possibly can about this muon, and then you use kinematics to infer what is the mass of the object that you've produced along with the muon. It doesn't matter that that doesn't have a mass. I can still ask the kinematics question because I'm measuring this muon and I can measure the properties of that. And that gives you a bound and says that if this object here had a well-defined mass, that mass would be less than something. The best type of measurement of this type is precision measurements of tritium beta decay. I think that's going to be one of the
way, I'll actually talk about that also next week. Yeah.
But so I won't say how that works because it's a great experiment. It's a very difficult experiment. But the point is, by measuring beta decay really precisely, you can ask if the thing that's emitted along with the electron and the proton has a non-zero mass. And we know that whatever is emitted is a linear combination of neutrinos with a well-defined mass. So the observable that you get at the end of the day, because the masses are very small, is a linear combination of the neutrino masses 1, 2, 3. So that object is often called the electron neutrino mass, which is not the mass of the electron neutrino, but it's a weighted average of the neutrino masses that we know. So if you take that number is less than 2 electron volts. I'm making this up, but it's approximately correct. So it's less than 2 electron volts. So we know that there's a weighted sum of the neutrino masses that's less than 2 electron volts. On the flip side, we've measured the differences of the neutrino masses squared. So we know that the difference of M3 squared and M1 squared is some number, and the difference between M2 squared and M1 squared is another number. And we also know that the weighted sum of the masses is less than something. So that means we have enough information to say that all of the neutrino masses are in some range. Because you can't be bigger than some number, and because you know what the differences are, you can't be less than some number either. And of course, you have to figure out what the ordering of the masses are, because the ordering of the masses will also impact what is your allowed ranges for what those masses are. So basically, you know, there are other observables that can see the neutrino mass, which are not oscillations. The other one is neutrinoless double beta decay, which maybe you'll talk about too. And that gives you another linear combination of neutrino masses, and you place a bound on that. And then finally, I guess we haven't talked about this, but there are also these cosmological bounds on the neutrino mass. We've mentioned this, and I don't think any of us will have time to go into the details of how that works, but you already have enough information to figure out qualitatively how that works. Because remember, Farinaldo said, if the neutrino masses added up to 90 electron volts, the neutrinos could be all the dark matter, right? Except that that's ruled out, even if we didn't know the neutrino masses, because the neutrinos would be hot dark matter. So if the sum of the neutrino masses were 90 electron volts, that idea would be ruled out by the fact that the neutrinos are hot dark matter. So as you start making the neutrino masses small, their contribution to the dark matter starts to go down. But remember, they are always the wrong kind of dark matter. So if their masses are too heavy, you have too much of the wrong kind of dark matter, and that's ruled out by the formation of structure. So by structure formation, we know that if the neutrino masses were like 20 electron volts, there would be no small structures in the universe. That's ruled out by observation. So you can keep doing this really well. The better you do this, the less the neutrinos can contribute to the dark matter. So that means that their masses have to be smaller and smaller. Everything I've just said is partially correct. It's a good way, hand-wavy way of understanding how these cosmic probes can see the neutrino mass. And usually one way of thinking about that is, by what you've learned here this week, you know that the neutrinos are hot dark matter, and you know hot dark matter is bad. And the heavier the neutrinos get, the more hot dark matter you have, so the more ruled out you are. So those experiments like to see the neutrino being lighter and lighter and lighter until at some point you see this effect of being less structure at small distances than you expect. And you say, aha, that's when the neutrino mass is. That's one way of thinking about that. Another fun thing about neutrinos is that they actually go non-relativistic today. So the cosmic neutrino background is not relativistic, which is kind of a crazy idea. But so you have these very, very slow neutrinos moving around. And early on, they were moving really fast at the speed of light. So at some point, they went from being relativistic to non-relativistic. And somehow when that happens, the universe knows about it. So you can also try to identify when that happens, and that will tell you what the neutrino mass is. Now, the reason I'm saying that is because, again, if you believe that result, you also learn something else about the neutrino masses. You learn that, given the precisions of the measurements we've made so far, you know that the sums of the masses are less than something. And again, if you combine that information with the oscillation information, you start to say more or less well-defined things about what the neutrino masses can be, because you know the differences and you know that they're not bigger than something. So if you wanted to make a periodic table of elements today, you could provide a lot more information about the mass of neutrino number 1, the mass of neutrino number 2, and the mass of neutrino number 3. That's one comment. The other one about these periodic tables, they're all wrong in a fundamental way, which I said. The electron neutrino is not a particle. It should not be on that table at all. The thing that has to be there is neutrino number 1, and neutrino number 2, and neutrino number 3. These are the particles, and these are the things you can label with a mass. And so that's hopefully how things will evolve, but we are very conservative, so things change very, very slowly. So anyway, that's...
Which is actually not that different for quarks. I mean, would have to be, quark masses are a little bit of a fishy thing.
Quark masses are also a very funny question, but we've grown accustomed to that.
Yeah.
No, especially the one with the animals is really nice. And if you updated that, we would know that all of them are ants. There are no badgers or squirrels or whatever floating around. They're all little tiny ants, which is a much more impressive picture, I think.
Comment is that everything you said about neutrinos not being dark matter is for the active neutrinos, right?
Absolutely. These are the only neutrinos we know exist.
Right.
The other one is very hypothetical.
Yes.
About this discussion, when we have a reaction like this and we measure the muon mass, and by kinematics we know what will be the muon neutrino mass, how come we don't have like something like quantum mechanics, like I measure mass 1 with some probability, mass 2, and mass 3, like 3 peaks, something like this?
This is a really good question, and it's all an issue of resolution. So it's a tricky question, but you could try to describe the process in the way that you've just talked about, is that you either have the pion going to a muon and neutrino number 1, or a pion going to a muon and neutrino number 2, the pion going to a muon and neutrino number 3. If that description were correct, then there should never be any neutrino oscillations, first of all, because you're killing off the neutrino oscillation by identifying them as eigenstate from the beginning. And we know that the neutrino oscillations happen. That means that something happened that prevented this picture from being correct. And it's related to the fact that the uncertainty principle doesn't allow you to say that. Somehow you don't know whether you emitted a neutrino 1, 2, or 3, so you've emitted all of them in a coherent way. When you measure, so that's, again, I said uncertainty principle. I meant if you were a perfect experimentalist that could measure everything perfectly, you would still not be able to make this measurement. The neutrino masses are too small. Again, you have to start asking questions like, how well can I measure the muon energy? And I can't measure the muon energy perfectly because the muon is not a stable particle. To measure somebody's energy perfectly, it takes an infinite amount of time, as you probably know. Closer to home, you have this pion, so you have to know your initial state, right? I mean, otherwise, you have to know that the pion is at rest. The pion is at resonance. Its mass, in quotes, is not well defined. It has a width because it decays. So you have to take that into account. And that's just the very, very basic fundamental physics things you have to worry about.
On decay, it's actually, with beta decay, it's probably easier to give the numbers because you know basically the absolute limit on these tritium decay experiments is 200 millielectron volts, which is of course much more than the energy splitting is. So you could go beyond that, but then you know you reach these quantum mechanical limits at some point. But even these highly precision experiments have a precision which is orders of magnitude bigger than the mass splitting.
Yeah, so by the way, for the tritium beta decay, when the electron comes out with a huge amount of energy, then you don't have a coherent neutrino emission anymore because you can in principle tell one from two from three. Now, if you go through the exercise very carefully, because the mass is very small, as you said correctly, in principle you have, in quotes, these peaks. In the case of beta decay, it's not peaks, it's spectra that end at different points. So you should be able to tell these kinks in the spectrum. Sadly, we don't claim that we'll ever get resolution to do that, so we see kind of an averaged out effect, and that's why we place a bound on some linear combination of the masses. So the averaging out effect gives you this observable.
I mean, it's being used for the 17 kV neutrino.
If the masses are heavy, that works quite well, yeah. But here it would be the same. And by the way, the same is true for the cosmology number, by the way. In principle, as I said, you should be able to see the three different neutrino species go non-relativistic at different times. So they should leave a complicated imprint on the history of the universe. But we have no hopes of being able to see that anytime soon. So that's why, you know, if you do the tritium beta decay very carefully, you can see how this observable comes about. And the other one that I should say is that if you didn't do my problem number one, you can see how difficult this thing is. Because if you measure the muon momentum at the part per million level, the bound on the neutrino mass is like 10 keV or something like that, or 100, I don't remember. It's in the really, really far away regime, because these measurements are just not the right way to do it. The masses are just too small.
There was a question. Yes.
So we saw that neutrinos, while propagating through the Earth, suffers matter effect, and that this affects the electronic flavor, right? But how about the presence of other stuff on the Earth, such nucleons that could like undergo neutral current effects?
Yeah. So so the answer is neutral current effects are there, but they don't impact oscillations because they affect all the different flavors in the same way. So the only exception would be if you look at, say, what Orlando talked about yesterday. If you're talking about a stereoneutrino has no neutral currents. So that means you should be able to see the impact of the neutrons in the matter. It turns out that there's neutral current effects from protons, electrons, and neutrons. And the protons and electrons cancel out. So only the neutrons matter if you're interested in matter effects that have something to do with stereoneutrinos. If you only care about the ordinary neutrinos, all the neutral current effects are not visible because they're proportional to the identity matrix. So they don't change the oscillations in a visible way. So you're only left with the charge current interaction with the electrons in the medium. If you had muons in the medium, life would be interesting, but that's not how the world works. So, and then of course the other thing I should say is, again, if you talk to your neutrino friends, they work on what's called as a non-standard neutrino interaction. These would be interactions which are new that you've just invented. And those interactions don't have to be the same for the muon, the electron, and the tau. So those would give you anomalous matter effects. And those are things you can look for in experiments like DUNE, for example. And it is one of these things that people spend a lot of time understanding is how do these non-standard interactions modify neutrino oscillations in a way that can be probed by the experiments. And that's one kind of new physics scenario that you can look for with, say, the DUNE experiment. And again, this is in the DUNE TDR. It will be, not there yet.
And if I remember well, we'll have a talk on non-standard neutrinos, so you can, yeah, on Friday, I think, or Thursday, yeah. Do you have a question?
If we have, suppose we have a precision to distinguish the neutrino masses, can we make a technology to measuring the mass and not in having precision and don't have precision and stop the oscillation and don't stop to give information to another place? It's possible one day.
So if I understood you correctly, this coherence question, you know, for having oscillations, that's not a technology question. It's is it quantum mechanically possible or not? So
Yes.
if you have a coherent neutrino beam, it will oscillate, and there's no measurement you can make in the laboratory ever to change that. So that's kind of the, again, quantum mechanical effects are not optional. They either are there or they're not there. They don't care how well you learned how to measure stuff, or whether you chose to do something or not. You know, oftentimes the world is measuring everything all the time, and if the world can't do it, then you can't do it in your laboratory either. So that's the...
Can I ask em português? Se você, quando a gente escolhe a precisão do experimento, se ele tem muita precisão, você tem, se você quebra a resistência da massa, você não tem mais oscilação. E se eu pudesse escolher um experimento, por exemplo, que eu ligo e desligo essa precisão, a pessoa que vai medir, ela vai medir ou oscilação ou não, dependendo se eu ligo ou desligo. Eu poderia usar algo desse tipo para mandar informação de um lado para o outro?
So this goes back to all of these quantum mechanics questions, right? So it goes back to questions you can ask. So I'll try to repeat the question. So he's asking about, what if I were in a scenario where I could measure, say, the muon momentum really precisely, and then collapse the neutrino wave function into one mass eigenstate or the other mass eigenstate? Then in that case, the neutrinos would never oscillate. But then if I didn't measure the muon, then this collapse would not happen, and then I would have oscillations. So in principle, I could do an experiment where I can turn the oscillations on and off by controlling whether I'm measuring the muon very precisely or not. So that's the question, right? If I understood it correctly.
Yes.
And my answer is, these questions, so first of all, this is a really slippery slope that leads to despair if you start worrying about that too much. But the answer is, in order for the neutrino beam to be coherent, it cannot be possible to do this, ever, even in principle. Even if you had a perfect experiment, that information is not attainable in principle because it's hidden because of quantum mechanics. So you will always have a coherent beam no matter what you're doing to the muon. So that's my position on this subject, and I think it's correct. And there are lots of ways of thinking about that. One is that this muon is hitting the rock, and it's depositing energy there. So I could argue that, you know, the rock has made the measurement for you really precisely. I don't know what the information is, but the atom that was hit by the neutrino knows. And why doesn't that collapse the wave function? And the reason it doesn't collapse is because it's not possible to collapse the wave function. My initial state, which is the pion that I started with, is such that this neutrino that gets produced is a coherent superposition of mass eigenstates. Whatever I do to this muon will never ever be able to change that. So I think that's the safe way of thinking about that. So it's not a matter of what you choose to do. It's the fact that there's nothing anybody could do to see this muon very, very precisely in order to collapse the wave function like that. And the reason for that is that the neutrino masses are really small. If the neutrino masses were 1 MeV, which is still a very small number, that would be a totally different world. If the neutrino masses were 1 MeV, there would never be any neutrino oscillations. They would always collapse. It's the same thing with the quarks. You know, when you have a charm meson decaying into either a kaon or a pion, it decays into either a kaon or a pion. It's never a linear superposition of kaon and pion. Now you could question, why is that? And the reason is you lose the coherence very, very effectively for lots of different reasons. So the neutrino system is special because the neutrino masses are really small, and it turns out that we have all these interesting sources of coherent neutrinos. So I think that's kind of I think that's the safest way of thinking about that. You shouldn't believe me, so I could be lying to you, but you should definitely be thinking about it to try to convince yourself one way or the other. This is a non-trivial question, but I think this is the right answer. But it's a complicated question.
Thank you.
So before we go to the next question, just clarification that maybe Orlando and Farinaldo can comment on too, because we've been talking about stereo neutrinos, and Orlando has shown results, possible indications from neutrino detectors, and probably Farinaldo will mention as neutrino, stereo neutrinos as dark matter, and those are quite different types of stereo neutrinos. As we saw in this morning, and as we saw during Orlando's lecture, the oscillation length depends on the mass, and actually when the mass increases, the oscillation length decreases. So for the stereo neutrinos that we would like for cosmology are those that we cannot measure, at least with the current technology, both for detecting and producing the neutrinos. We cannot detect the oscillations of the cosmologically interesting stereo neutrinos, correct me if I'm wrong, and those that we are maybe finding some evidences or indications in the oscillation experiments are not those that solve our puzzles in cosmology. So just if you want to comment on that,
I completely agree. So the stereo neutrinos that could be dark matter can be as heavy as 1 TeV or 10 to 11, 10 to 10 GeV if you want. So it has nothing to do with the neutrinos. These stereo neutrinos you're looking at with reactors, for instance. Nothing. So the stereo neutrinos that we often talk about as dark matter candidates might be related to explaining neutrino masses, but not the oscillation, not having any effect with the oscillation of the active neutrinos, So the stereo neutrinos that can be dark matter can explain why the neutrino masses are so small, but has no interference with the neutrino oscillations. Okay? So they're different in this aspect.
You want to comment?
Okay, more or less to repeat, you say the stereo neutrinos that you use, that you look in the oscillations are very small masses, very small mass difference. And then the physics is completely different, what you expect from this in the cosmology. But then I wanted to make something like teasing to say. Yesterday I put it like they say the NES, the stereo neutrinos are a linear combination, union, unity 4. And me or also Andrés say very clearly, okay, one thing is stereo neutrino, the other thing is the heavy nu 4. But then you call stereo neutrino in cosmology. Is a stereo neutrino is a massive state, or the stereo neutrino, they say, what is this?
Do you want to comment on that? Or?
I mean, again, this is, it's useful for thinking about this. Again, the particles are always the things that have mass. The interaction states are linear combinations of those. But if you always think about the particles as the things that have mass, you'll never get it wrong. So that's kind of a very safe message is that we can always talk about the interaction states, the nu e, the nu mu, the nu tau, the new stereo that maybe has some new secret interactions with the dark matter, blah, blah, blah. But the things that we always constrain in the laboratory are these neutrinos with a well-defined mass, including the dark matter. The dark matter would be a linear superposition of the electron neutrino, the mu neutrino, the tau neutrino, and the 20 stereo neutrinos that you've invented. But it's a state with a well-defined mass. And what this E, mu, tau, all of these different labels that we say these things are a linear combination of, that's kind of a shorthand notation to describe how these things interact and what kind of couplings they have. So that's probably the safest way of always thinking about these things, especially in the context of cosmology and astrophysics, where these things stick around for a long time. And everything that sticks around for a long time always ends up looking like a bunch of mass eigenstates. So the coherence is long lost, and it just looks like a bunch of mass eigenstates moving along, doing their own thing, and they don't remember this thing of muon, tau, electron, and so on.
We have time for one question. Okay, good. I think we explored lots of questions. So we will go to the coffee break. We reconvene here in half an hour. And then today we'll make a slightly different way of doing the exercise session in a way that we'll be able to interact more with the lectures. So we'll split the class, and I'll give more details when we are back from lunch. Okay, thanks. 30 minutes coffee break, yes, not lunch. Thanks.
A Carla está vendo agora no laboratório? Bom, você pode dar para ele.
Okay, so we'll start. Well, before we start with the exercise session that I will describe right now, again, perhaps I'll give the message to the wrong people because you are here, right? But I'm really concerned. I know most of people have been attending everything, so again, maybe I complain to the wrong people. But I'm a bit concerned because at the early, at 9 o'clock, 9:30, sorry. Not everybody is here, so that's very important. And sometimes, apparently, some people consistently is not showing up. So there are 3 reasons for which we are passing this presence list. I know this is annoying, right? But there is a practical question that we want to upgrade everyone that's here, even those that didn't have room. So we need to know really who's missing. I mean, there's people that didn't register. Okay, these are missing, but some people didn't sign for 3 sessions. So even if they are here, maybe they shouldn't do this practical session, right? So there is this practical question. There is an ethical question that we are using public money, taking extra time of the speakers and everyone. So this has a very heavy cost, not only in money. So students that are funded, or even those that are not funded, this has a cost. So we really want people to be participating. Again, I know most people are just participating because they want, but it's not like in grad school or in university. University, I don't care if a student's there or not, because there is an opportunity to learn, and there is at the end there is the exams and so on. So the learning process is a long thing, and if the student doesn't show up, that's not, for me, it's not a big deal. But here, the learning process is just here. Then you go away from home, right? So we really want you to be, present, so that's the ethical part. And there's a pedagogical part about arriving in time and being responsible and so on. You are all grown-ups, but still, just after teenagehood. So there's a pedagogical thing. And there is a physics thing that maybe it's interesting to discuss, right? So some of you saw this plot, but most things in nature are probabilistic, either because of fundamental reasons like quantum mechanics, or just because many things add up, and at the end they are probabilistic. Like the time you arrive to some place, it's clear probabilistic, right? Because you get to the metro and the metro just left, and you need to wait all the metro, or you're lucky and you arrive and the metro's there. So the more steps there are, the more the possibilities of things being different each day. So there is a probability distribution. So if you leave at TD from your hotel, there is a 0 probability that you will arrive before the speed of light divided by the length divided by the speed of light, right? So this is really starts, here's 0. You cannot arrive before that. And probably if you just walk by and get here by walking, then there is like another time, that after that it's very unlikely unless you break a bone or something. So there's a probability distribution like this, and usually has a tail, right? Because, delay, you never get before that time for physical reasons, and there are many things that can delay you. But there is a probability distribution. I hope you all understand that, right? So again, if you plan to be in the mean, right, at the right time, you will screw up all these times. So really, plan to arrive ahead so that most of the time you'll be before the time. So you have to plan this distribution, the peak, to be before the time the classes start. That's the deal, right? Plan to arrive earlier so that most of the time you get in time, right? Okay, so this being said...